Good afternoon. Had a good lunch? Okay. Who is first time at Øredev? Yeah, majority. That's very good. My name is Vagif and I work at Norwegian Broadcasting Corporation. It's analog of Swedish TV, like SVT. I also play keyboard in the band Line Breakers, who's going to have a gig tomorrow. After party, we sing about IT with some twisted lyrics. But you will recognize all the songs, so please come and join us. I was here 2 years ago with my co-speaker. We were talking about what you can choose in .NET development, F# or C#. My co-speaker, Max, he was advocating for C# and I was advocating for functional programming and F# as viable alternative sometimes, which can give you some advantages. And today we're going to look at other alternative to like mainstream object-oriented development in C#. Who is doing object-oriented development in C#? Yeah, almost everyone. And this time you won't need to leave the language. You will do it in C#. It's just you will implement your objects differently using so-called actor model. So this presentation is rather short. It's just 40 minutes. And I have material maybe for 1 hour or even more. So I need to figure out what to focus mostly on. And then I need your help. So why are you here? Are you here because you're already using the actor model and just want to learn more and maybe look at some details? Who is here for that reason? Nobody. Who is here because you're... you are. Who is here because you're familiar with actor model concept and may consider it, but just need maybe more information about it? Yeah, maybe half. And who is here because of curiosity? Like you haven't really read about actor model, but you know it's maybe an interesting concept. And of course, all good things start with curiosity, and actor model is a good thing. Who is here for that reason? Okay, probably more than half. Yeah. So I think I'm getting a picture where I should focus on. So we can't just jump into libraries and looking at different open source projects in .NET. We'll start with a small teaser. So this is a very simple C# code which uses some sort of library which implements mammals and animals. We create an instance of a dog, and then we call method bark, and of course the class dog has obligatory method bark because all dogs bark. What can go wrong with this class? Just it's very simple. It looks like completely innocent. I mean, is there anything you need to like think of if you bring it in your system? Any ideas? What if I show you this using animals.concurrent? Will it give you some clue about what can go wrong with this one? Probably, like if you use it multi-threaded environment, in concurrent environment, we often ask, is the thread safe? Like system.collections, is the thread safe? No. System.collections concurrent. Okay, we can use it in any multi-threaded environment. So, and we work majority of our time, I guess most of us, with an environment where we need to think about concurrency, need to think about parallel execution, and actor model can actually take away, solve these concerns for us without sacrificing scalability and performance, which is very important. So, we're going to have a look at why every developer should become familiar with the actor model and what .NET gives us in terms of actor model frameworks and libraries. And I will show you some sample code generated using AI because, of course, every talk needs to touch AI. And since I work closely with one of the libraries, Akka.NET, I thought it would be unfair if I write good code using Akka.NET and then maybe code of lower quality using other libraries. So, okay, let AI write all code for me. Bonus, which I don't think we'll have time, I can tell you some about my team experience and how we use Akka.NET at NRK in a mission-critical product, but if I don't have time, you can just ask me offline. So, actor model for developers. So actors can become behavioral units of your application. And that's slightly different from traditional C# classes, where they are both behavioral and structural units, like they contain data for your applications. Actors can also become deployment units of your system, and they have a very good property, location transparency. So you can just write your system using actors on a local machine, and then use exactly the same code, just different configuration, and your cluster nodes spread around the globe. So, most of you, I guess, familiar with solid principles, where S stands for single responsibility, O, open close, L list of substitution principles, I, of course, for interfaces, and D, dependency injection principle. Yeah, correct. And you see what these principles actually don't teach you. How you learn to write code, write your classes that will safely communicate with each other in multi-threaded environments, in concurrent environment. And so it's mostly focused on like statically designed code, like how do you design your beautiful class hierarchies and interfaces. But the way OOP is implemented in popular object-oriented languages, I don't think it reflects physical and physiological processes, and we'll say more about that. So, we're living in the epoch after the Moore's law. We won't have time to go into details of Moore's law. Who is like briefly familiar with what Moore's law? A majority of you. So again, if we sort of simplify it, like law was formulated about 60 years ago, and it stated that every 2 years, then it was corrected to every 18 months, your computer power basically will be doubled. So the same application will run twice as fast in 2 years. You just upgrade hardware. And of course, that had a significant impact on how we program. Okay, you just write the code, and in 2 years you run it on a better machine. It will become twice as fast. And it doesn't work this way anymore. If you look at this diagram, you see that frequency has stabilized. It's flattened around 2005. But what actually is growing now is number of logical cores. So demand for concurrent execution of our code is much stronger than it used to be. And requirements to IT systems also much stronger. If you look at typical specifications of IT systems 25, 30 years ago, large system comprised of 100 servers, and response time of 1 second was okay, with some maintenance downtime, like a couple of hours a month. And if you look today, then you run clusters and you can have like tens of thousands nodes of cluster, and then response time is 1,000 times shorter than it used to be, and we expect to have no downtime. So it's completely different requirements to IT systems. And it's that requirement, another law becomes very important. It's called Amdahl's law, which was formulated around the same time as Moore formulated his own. Probably few people familiar with Amdahl's law. Yeah, very few people. But again, we won't have time to go into details, but what it did, Gene Amdahl did, he's actually specified numerical dependency between how big part of your application can be parallelized, and how much of performance gain you will have if you increase number of CPUs. And of course, if 100% of your code can be run in parallel, then by increasing number of CPUs by 10, 100, 1,000, you increase your throughput accordingly. But there is an eye-opener actually, that if 60% still, most of majority sort of most of part of the code can be parallelized, then you don't really need to invest much in increasing number of CPUs, because you soon reach your limit, your performance limit of your system. And, oops, this doesn't, there was a, okay, let me see. There was a video which unfortunately doesn't play. It was a video from Chinese highway. I think around a month ago there was a video that showed a lot of cars. I think it's 32 lanes. They coming to toll station, and then you know what happens there. There is a big queue, and this is actually a very good illustration of Amdahl's law, like traffic, where you have tens of lanes which just squeeze into very few. So, and traditional OP, it may sound like a bold statement, but it doesn't match real-world processes. Term OP was coined by Alan Kay around 90s, and then he later said that I made up the term object-oriented, and I can tell you I didn't have C++ in mind, which means that he didn't have in mind C# or Java either. So traditional OP emphasizes design of class hierarchies with very little focus on how different objects interact in concurrent environment. And if you look back on actually what he meant with OP, actually his view of OP was that it was very much influenced by biological systems. So objects were like mini computers. They didn't expose its state. They didn't expose getters and setters, which is unnatural in the real world. And they communicated by sending messages between each other. So if you look back on this dog example, you see we're creating an instance of the dog and then calling my dog bark. Who is calling my dog bark? It's not the dog itself. Doesn't it sound unnatural? So there is some dog manager, dog controller, dog whatever, is calling from a different thread, dog.bark. So, I mean, it's a puppet dog, basically. It's dog without life. It's a dead dog. I mean, it's like a dead parrot in Monty Python's cage. Don't you agree that this is unnatural to model at least animals in such a way? So, like here, if dog will be called from different threads. One thread asking dog to bark in some of Slavic languages, half. Another one, it asks about woof woof. What will happen to the dog? Since it doesn't using animals dot concurrent, just regular animals, probably the dog will crash. And I don't think you should turn yourself into defensive mood. And try to defend that it's natural. No, it is not. It's just that when we design computer systems, we don't always need to model things just like they exist in real-world processes, because this computer doesn't look like anything human, but it solves great tasks. It's just that sometimes there are scenarios that may require different thinking. And when we have this OP hammer, then we try to solve all tasks pretending that this is how implementation should look. For example, in game development, where you have different characters, there are independent objects which rather work independently without some character controller calling them. So if you look at classic business objects, then you have account and you have debit and credit. Of course, your account will be ruined if you allow to access it simultaneously from different threads. So what you do, you typically lock bank account. So if you run credits and debits, then they're executed sequentially if this transaction is between two same accounts. So, but locks do not compose. You see, you have to place a lot of locks, but unlike class libraries, you have many nice class libraries and you build a bigger system from it. If you have a system with a lot of locks placed and then you expand the system, usually it requires revision of your locks. So which means that the multi-threading, the locking, it's hard. And then if you don't implement it properly, you become a victim of Amdahl's law. So you throw a lot of new CPUs, but your performance doesn't improve. So what if every object had a dedicated thread? So it wouldn't have any problems with concurrent access. Of course, this is very naive. We can't do that because threads are expensive and the number is limited. But what reactive program is dealing with is like objects are awakened and they use computer power only when they get some messages. So we don't need actually to pre-assign thread to an object. An object may lease a thread during message processing. So if you have bank system management, then you may lease a thread that will run certain transaction. In real system, probably you will also need to have a thread per bank account, so it will be more complicated. But the idea is like this: so you don't have some dispatchers or controllers which do a lot of locking. You sort of solve it by giving power to self-running objects. So this is basically foundation of the actor model. It's more than 50 years old, but it became popular just maybe last decade, partly because of Moore's law wasn't really applicable anymore, and Amdahl's law became much more important. So everything is an actor. It's similar to OP concept that everything is an object. But OP object combines structure and behavior, while actors, they only model behavior. So what can an actor do? An actor can create new actors. Of course, send messages to other actors. This is the most important what an actor can do. It can receive, since it can send, it can also receive messages one at a time, messages from other actors, and it can change its internal state. But you can't access its internal state directly. How do you get data from actors? You can send a message, like, give me some information. It may send you something back. This is how you implement it. So this is an actor hierarchy. And these are messages that actors send between each other. So, actors versus objects in traditional OP. So, actors represent reactive programming. So, actor stays most of its life in a deep sleep. And when it's awakened, it has sole control over its state and behavior. So, an actor dog will get a message like bark or please bark. But this message, it's not like a method call which immediately executes some operations. No, it's just a message, and then it decides, depending on its internal state, what it does with a message. And with my dog, I don't even need to send a message to it. He barks a lot without messages. Yeah, so he owns the state. And also, well-managed actors, they don't bother other actors with questions, even though most of actor model framework, they have like tell and ask operations. You can ask something, and then it's a model operation. You went for an answer. You're waiting for an answer. But I think this is anti-pattern, which should be avoided. Just implement everything using one direction, single directional messages. So when it comes to deployment, actors respect the first law of distributed object design, formulated by Martin Fowler, which says that don't distribute your objects. So with actors, you don't split, you don't divide its state into multiple processes, machines, or nodes. You know, it lives in one place. Like bank account actor lives in one place, and when you receive the message, there is a single thread that is responsible to handle this message. And this is contrary to many failed attempts by changing OP in a way that we could magically call .get name for an object that lives somewhere in Australia. So all these attempts, like RPC, Corba, DCOM, they were not successful. But when the only thing you have is just sending messages, then it gives you location transparency. You implement your code, you just configure where the actors live, and then messages will be delivered wherever it lives. And it's actor model framework that takes care of it. So actors can be persistent, and persistent actors based on event sourcing in some classical implementation. So when actor is awakened, it will read its messages, it will replace them, and it will read its state. And in distributed systems, actors provide a great choice for distributed systems that require high scalability and low latency. And this is because it's just unidirectional messages. And you can configure actors that they run in nodes that can form clusters. And actors framework, out of the box, they provide you some popular deployment choices. Like you can configure actors as a router. We will have a look at one of those. So let's say you send something to cloud storage, and then you won't have throttling, like so many simultaneous workers should work. Then you implement a router of n. Then actors may be configured as singletons. Actors may be configured as cluster shards, typically in bank account management. Every, of course, bank account is kind of singleton. So you implement it using cluster sharding. So, and designing actors require change of mindset, because like every resource is an actor. So it's customer, bank account, file set, file. Actors are very cheap. And they, while they're asleep, they don't consume any resources. So think about every resource as an actor. And so the change of mindset, that you should try to go from this focusing on managers, controllers, dispatchers, to make your actors more independent, self-running. And then you should tell them what to do, don't ask. So if we illustrate it on a simple example, and this is actually what we are doing at NRK, we are publishing a lot of media files to the cloud. So we have a file dispatcher which reads things from message queue, and every message contains, let's say, reference to a file. And then we need to upload them to cloud storage. So turning this into application that will use actor model. First of all, every file will be an actor. In reality, it will be even more complicated, because probably file set will also be an actor. You have a file set which consists of files of different qualities, but let's don't sort of make it complicated now. So we dedicate an actor per file, and this we will use in our example shortly. And we want to restrict number of concurrent workers which talk to the cloud. So we have a router of n. So we don't send stuff directly to the cloud. We send them to a router. We send a message, upload the file, and then a router takes care of it. So there are languages and frameworks that favor the actor model. And there are languages actually that tailored to support actor model. It's like Erlang, Elixir, Pony. Scala is not built for actor model, but one of the most popular actor model frameworks, Akka, was originally written for Scala, and Scala partly became very popular because of that. And since we are in .NET, then there is Akka.NET, which is a port of JVM Akka to .NET, which has both C# and F# API. There is Microsoft Orleans. They don't use word actor, but essentially it's an actor model framework. There is a Proto-Actor, which is a Swedish open source project. And F# mailbox processor, I think it's mainly if you want to experiment with actors in F#. So, what are viable choices in 2025? Microsoft Orleans. It has most number of downloads. Now I think it's 25 millions. Akka.NET, it's around 20 millions. And Proto-Actor, it's just 2 millions, but it's very stable and mature product. And Akka.NET is most active in terms of support and maintenance. You have releases all the time, and they have very good community. So Microsoft Orleans is released about 10 years ago. And it powered as a cloud services for Halo. So that's for game development, actually. It has C# API. It used to have a community F# API, but it's now discontinued. And it deviates from traditional actor model. They don't use word actor. They call it grain. They also have concept of silos. Grains always exist. You don't control lifetime of actors. And then they try to encapsulate it as POCO, as just plain old C# objects. So you don't need to think that you send messages. You're just calling methods, which I think I'd rather be explicit about sending message. But if you prefer POCO, this is for you. Akka.NET, it actually was released around the same time as Microsoft Orleans, and it has both C# and F# API. Actually, there are two F# APIs. One is official, one is community. It supports HOCON configuration, which was inherited from JVM implementation, but it didn't really look at home in .NET development. So now it supports iHost Builder, configuration builder. So it's you just bootstrap it like .NET services. It's like classical actor model framework. It supports actor hierarchies. It supports actor supervision. Of course, like Orleans, it has support clusters. They all have location transparency. And also there are support plans. There is add-on packages. But even if you use it like free version of it, they're excellent in answering your questions on Discord. Proto-actor. It's actually originated by co-founder of Akka.NET, Roger Johansson. And it's been in beta almost for 5 years, but actually it was very stable. And it has API for C#, Go, and Kotlin. And this is a smaller team, a sort of smaller product. So they try to apply don't reinvent the wheel philosophy. So instead of, like with Microsoft Orleans and Akka.NET, you implement your application using that framework. It's a foundation of your application. With Proto-actor, it's more like you have some islands in your system where using actor model makes much sense. And they try to reuse standard protocols and cluster discovery tools. So it's they also have a support plan. It's a very stable product. Give it a try. So very opinionated selection guide. All these selection guides, they are opinionated, so it's my personal view of this. Like, why would you choose Orleans? They use virtual actors like grains and without explicit lifetime management. So somebody said that, Orleans is like C# while Akka is like C++, like you have explicit control of actors there. So if you prefer that, Orleans is for you. Then they favor actually traditional OP over one-way messaging, which I personally don't buy. But again, if you would like to use traditional methods, async methods, this is for you. And of course, there are some organizations that prefer using Microsoft products, so that can also be argument, like organizational reason. Why choose Akka.NET? It has huge community because you can use, when asking questions on Stack Overflow, you can ask people working in Akka with Java and you will get questions because it's just a port of Akka on JVM, even though a lot has been changed. It has fine-grained control of actor lifecycle. Then it has explicit message sending APIs like tell and ask, even though you shouldn't use ask. So it's not wrapped into nicely domain-specific message calls. Persistence based on event sourcing, which I think is a great thing. They have also F# API for functional programming lovers and excellent support from maintainers. Finally, why choose Proto-actor? As Roger Johansson said, that he tried to write it without backward compatibility compromises. Like it's a clean new actor library. And then, as also it's quote from him, you can use actors in isolated islands over distributed monoliths. So probably if you want to give a try the actor model, that's actually a nice start. Also, they use Google Protobuf, so all messages are sort of remote by default. And they use existing clustering providers like Consul, Zookeeper, native Kubernetes API. And of course, we are in Sweden. so we couldn't omit this library. So what I did then, I asked Google Gemini to generate, to rewrite file upload dispatch using different Akka frameworks. So if you want code for this demo, because we won't have much time on going through the code, so this is a QR code. It's in my GitHub repository. So let's have a look at the prompt. Prompt is very important because what I did, I wrote small console application which was uploading files to the cloud, and then I asked, without specifying what exactly to do, can you just rewrite it using the actor model? And then what it did, it wrote me Akka.NET application, but basically the whole console code was put into the body of an actor. So the actor just received message with with the file array and just in a loop just start this upload, which basically proved the fact that you should be you should care about your prompt and you should act as an architect. Like, don't assume that AI will make decisions for you. Maybe in a few years, yes, but yeah, I generated this code around like 1 month ago, probably. So that was a prompt. So generate code in C#. It's a console application, and it should read a list of files and upload them to Amazon S3 storage using some actor model library. So first requirement, and it's about reference. I had C# file, which just I will show you in a console application, which did the job. It's relatively a simple file, and then it should be used as a reference. Then application should be rewritten, and it should take a single command line argument, file name of a document that contains a list of all paths. And each of item is one file that is uploaded to Amazon S3 storage. And this is sort of architecture choice. So upload should be run in 2 phases. First, we need to create one actor per file. So it should send messages to file actors. And these file actors should further communicate with using pool router with size of 10. So there are like 10 routines that talk to our cloud storage, and these are received messages from our file actors. So let's have a quick look at the code. We have something like 8 minutes to go. So this is original S3 uploader. So yeah, we read a file which contains a list of files, and then we create Amazon client, and then it's just for each file path and file paths. We use file transfer utility, is offered by Amazon S3 API, and we upload the files. So if you look at how Akka.NET implementation works. So here we create an actor system, and then we create actor pool of S3 actors. It's a pool of T. So you see, if you look here, we asked actor model framework to create S3 actors with router new round-robin pool of T. So there are different strategies which we can use when creating routines, and this is one of the simplest ones. That's just round-robin. And then for each file, we create file actor, and then file actor tell. And when file actor, if you look here, here is file actor. So it it's a message handler for the message of type file path. So we receive file path, and then we just forward it S3 actor pool tell. So this is how we implement this 2-phase upload using Akka.NET. If you look at with Proto Actor, we probably won't have time for it, but it looks very similar. It's just different API. Orleans actually looks a bit different because they don't use word actor, and actually I had to tailor a little bit prompt. Also I had to fight with different Orleans version because it was trying to mix different versions, but eventually it compiled, and then you see it tries to implement everything like object oriented. You have file grain, which implement grain with string key. You have S3 grain with integer key. It's like a router with round robin, so it's a number of grain. And then internally just send message, but they call it like process file, upload file. So they try to use the code like this is like regular C# API. And then, so when you start the program, you create your Silo builder. You have you bootstrap your system, and then you do the same thing. You just get grain, and then you send message process file. And in process file, if you go to grains, there is a file S3 grain. Okay, here it is. Yeah, process file. What it does, it forwards message to S3 grain. Yeah, and with proto-actor, just to quickly show you, it's actually very similar to akka.net. Yeah, so this is our S3 actor, and this is file actor, and then we create we create new round robin pool with number of T. Yeah, so it's very similar to akka. So actually we have a few minutes because what I was showing you roughly, actually it's what we're doing at NRK. We use them for media file distribution, and unfortunately this video doesn't work either. That's silly. Okay, because that was a dashboard of our system with hundreds of actors, hundreds of files uploaded. So I just wanted to show how, at that time there was a batch we received of several thousand TV programs which we had to upload, and that you see that on this dashboard everything is working simultaneously, and the whole system doesn't have a single word. You will won't find word thread or lock in our system. It's all using the actor model. So, okay, let me try to go. Yeah, so our technical stack, we're using akka.net. We use F#, but of course you can use C#. We use Ackling, akka.net, F# API, using RabbitMQ, Service Bus, SQL, and NoSQL databases. So, to summarize, why should you look at the actor model? So, it's about proper modeling of real-world processes and interactions. And if your scenario, if your domain actually requires that, if it will benefit from that, then the actors can be a way to go. It has very simple threading model. Actors work as finite state machines. They really shine when it comes to scalability performance, and also they provide great resilience. You have so-called actor supervision, like when child actor crashes, the supervisor, the parent actor is notified, and it can make a decision about what to do with that. So yeah, with that we have 2 minutes to go, and this is what I had in my list. We have maybe time for 1 or 2 questions, please, if you have. Let me ask you, do you agree that it's a bold statement again that a traditional C# or object or OP, it doesn't really correspond. It's not good for modeling biological processes. Like modeling dog this way is it's silly. Who disagrees with that? Who agrees with that? Yeah. So I probably confused it because like 4 people agreed, nobody's agreed. And the rest of you probably are in deep thinking about it, which is again a very good thing because it's about curiosity and about maybe we will make some consideration when I go back and check your project. So it's any questions? Okay. No. No, unfortunately, no. If you have two systems, they need to communicate using standard transport. Oh well, standard or not standard. Well, some other transports like service bus, RabbitMQ, but they can't. The message protocols aren't compatible between them. Okay, then enjoy the rest of the conference and please come to the geek party tomorrow and have a nice time. Thank you.